Hello, everybody. Welcome to the first machine learning seminar this year. Happy New Year to everybody. And I'm very happy to welcome Dr. Tjeerd V Scheper from the School of Engineering, Computing and Mathematics, Oxford Brookes University, who will present us the topic on criticality analysis for nonlinear data representation. So Tjeerd, the floor is yours. If you could introduce yourself better than I did, that would be great as well. And you can ask questions along the presentation if the time allows us first.
Yes, that's fine. Thank you. Well, thank you. Can I first start by thanking Jakub and Stefan for inviting me, and I'm pleased to present to all of you. And I have a little bit of a story to tell. So I've got a set of slides where I try to get to the point where I think you have a good understanding of what I'm talking about when I'm talking about criticality analysis. But feel free to interrupt me if I'm not being very clear. As we will see, I will skip some of the slides depending on time being left, but I'm happy to answer questions or go back if things are not clear, so please let me know. Okay, very quickly, just a single slide, a little bit of background. So my name is Tjeerd V. I'm Dutch, but I work in Oxford Brookes University, and I'm the group leader for the Artificial Intelligence and Robotics Research Group, which has several members in it who have a variety of different interests in the area of robotics and AI. And specifically, what I'm interested in is the aspects of bio-inspired computing, with particular interest to dynamic systems theory and how this is used in biological systems to solve problems. And then I aim to use that information, that understanding gained from this study to solve problems in health and life science, robotics and engineering, as we will see in a moment. I've been doing this for quite a while, and this is the reason why I've got a bit of a story to tell, because as you will see, different elements are built up from previous work, and I hope that when you go through the journey with me, that it's clear of why I need to go to seemingly random tangents, but it all makes sense, I hope, in the end. At the end, I also will introduce a new concept that I've been recently been working for in a single slide for you to ponder about. And I hope that might sort of start some conversations and some discussions that might be of interest to you as well. So let me just give you an outline of what I will be talking about. First, I will introduce you to a concept called rate control of chaos that I invented quite some time ago nowadays. And what this has to do with machine learning, I hope will come clear as well. Then I introduce you to self-organized criticality and how this applies in this context. And then we'll talk to the meat of this lecture, which is about nonlinear data representation and why this is a useful thing. And I will end up with a more recent work performed by my research student, Tjeerd V about the use of this method for human gait analysis. So let me start by talking about rate control of chaos. Now, normally I would go into quite a long explanation of what actually chaos is and what does this mean, but let me just briefly summarize this by saying chaos is a property of nonlinear systems where the system is unstable but deterministically contained within a codic attractor. And some of the properties of it mean that even though the system is unstable and you don't know, due to the principle of the butterfly effect, namely the sensitive dependence on initial conditions, where the system will end up. But what you do know is that it will always remain within the attracting space. Now, the idea of rate control of chaos is very simply based on this idea of where you have here illustration of a mapping, a chaotic map in this case, where the equations don't describe that, but this is just an illustration of illustrative figure, where when you apply an evolution in time of the chaotic map, the rate of expansion of this chaotic map is different in different types of directions in which it evolves. And this is similar to the idea, for example, in a normal linear space where you have an evolution in time which changes in different directions at different rates. But of course, in a chaotic system, this happens at an exponential rate rather than a linear rate. So you can sort of imagine in normal cases, your system that starts here, starts here in the middle, would evolve by expanding at different rates in different directions. So the shape of this sphere changes in an exponential way rather than a linear way. The idea of the rate control chaos is basically saying, well, if we can control the rate at which this expands, we can limit this expansion and thereby preventing the system from becoming chaotic. So below here in these equations, this describes the standard default Russell model, which is basically a three-dimensional model, a reduced model of a chaotic system. And it has only one point of nonlinearity down here in the third equation. And we apply this sigma rate control function, which is basically based on this idea that the proportion of expansion of one evolution in of one variable in time is proportional to the rate of the space that it can occupy in space. And then we limit it using this exponential function. So if we apply this particular rate control function on the system with appropriately chosen parameters, what you basically can do is this. Instead of having a chaotic model, and you can see here the thick line shows you the stable control system. If we plot the rate control function itself, sigma, you will see that sigma will oscillate in this case around the value 1. It means, of course, that if the rate control is not enabled or if the system is not expanding exponentially, it has no effect on the control, has no effect on the evolution of the system, but it will basically respond if the system starts to grow or shrink exponentially by reducing or increasing the rate at which this particular nonlinear term grows. So that's basically the idea behind rate control of chaos. Now, this is very effective, and I've applied this method to lots of different chaotic systems, and it always has a good way of being used for this system. Another example here is the more famous relevance system, which are the three equations here at the bottom, the x1, that should be z, of course, sorry. Equations. And we have here two rate control equations, which look a little bit complicated, but in effect, what they do is they are applied to the two parts of the nonlinear growth of this model. Now, if you apply this rate control chaos to the relevance model, normally you get in green here the normal cloud of the famous Lorentz butterfly shape. But if you apply this control chaos on this system, you can see here in blue how it stabilizes this particular system into a stable orbit. How this then shows in time. On the right here, we have a plot of the z variable in time over the evolution. First you see chaos, and at time step 50, we enable the control method, and it takes a while to stabilize, but once it stabilizes, you can see it becomes a nice stable orbit. What people often don't realize about the Lorentz system is that it has actually different modes. The row variable, the row parameter of the equation is actually a bifurcation parameter, and depending on what values you assign to this row parameter, it will have different shapes. And here in blue, we have the classic butterfly shape plotted against the, in this case, we are plotting the x versus the z variable of the Lorentz model. you have the, let's say, blue shape, but depending on the value of this row parameter, you can also have other shapes of this attractor. And the top one, we have one which actually has two different modes. There's a coexistence of two attractors in this space. You have this twisted shape here, but there's also the mirror image that coexists at the same time as well, which I haven't plotted here because that makes it more difficult. But even independently of this different mode, using this method rate control chaos, you can still stabilize different orbits and even multi-orbits within the same space. If we look a little bit more detail here, what you can see is that if we again look at the rate control function, enable it again at time step 50 in the middle here, you can see it nicely stabilizes this variable as well. But on the right, we can see something more interesting, namely where the rate control function is plotted here on the x-axis versus the y-axis in the left image. But we plotted this against the local Lyapunov exponent estimate. Now, the Lyapunov exponent estimate is basically a method to estimate at what rate the local system grows at an exponential rate. And if that is 0, that means it's in a stable state. If it's negative, it contracts. And if it's positive, it grows. And if the positive is more than exponential rate, more in a chaotic system, that would be grow faster than 1. Now, interesting here, what you see here, this is the plot of the control function versus this Lyapunov exponent estimate. And you can see that the system actually is stable, but is still slightly positive. It means it still has properties of chaotic behavior in it. And that is because the estimate is calculated by creating a small local perturbation and basically exploring what happens if you have a sensitive dependence of initial conditions and then you basically measure how fast the perturbed system grows in relation to the normal system. Okay, there was a lot of
yeah,
is a question?
Yes, to understand better this rate control of chaos idea.
Yeah.
So what is the purpose of this? Do you want to control the chaotic system such that you will limit this attractor domain, or you want to make it as non-chaotic as possible? And neither. Yes.
Aim is simply to cause the system to not grow exponentially. So if I just go back 2 slides here, if you look at the stable orbit contained within the Reservoir model, what you see is that's actually contained within the chaotic attractor in this case. So basically, what you have is a method that stabilizes the chaotic system to become, in this case, periodic behavior rather than chaotic behavior, and without changing the properties of the actual underlying system. Now, if you look in literature, you'll find dozens of different methods of chaotic control, all of which are actually based on 3 different methods of control, but they all either aim to prevent chaos from happening, actually removing the chaos from the system. That is one solution you can do to get rid of chaos. Or by having, for example, using time-delayed feedback, or basically changing the local properties of the chaotic system such that the system remains near a particular orbit that's already contained in the system. The rate control of chaos system doesn't do that. It basically, because it's also a feed-forward method of nonlinear control, so it doesn't depend on any paths of feature predictions. It only uses the instantaneous values of the variables. And it basically aims to control how the system evolves to to space, to the physical phase space, and prevent the system from becoming unstable. That's the whole aim of the exercise.
Okay, now it's much clearer to me. Thank you.
Okay. Thank you. Please, if you have any more questions, please let me know, because I know it's new for a lot of people. Now, this principle has been used for different types of applications. We applied it to bioreactors, wind turbines, and different things. We have a very interesting physical demonstration to show that this method actually works in the physical system as well, based on a combustion engine. So we actually took a diesel engine, took out the electronic control unit, and basically treated the engine as a dynamic system and controlled the behavior of the engine just based on the angular velocity of the crankshaft. And I think that's quite nice proof that the method actually works in practice. And we have a patent on this to demonstrate that there are direct practical applications. But this is not the core of what I want to talk about today. This is just a bit of background, and this background is important because this is core to the next bit, is the method can be used for different applications as well, not just as a nonlinear control method. Let me introduce you to another concept in physics, actually, but it's also important in biology, known as self-organized criticality. Now, what is self-organized criticality? It's a property of physical systems that depend on lots of components that are in interactions with in a local behavior due to nonlinear type of dynamics. And this is often illustrated by what is known as the Senpile model, but it's only one particular type of way this can be represented. It's the same idea that lies behind why avalanches happen, or why other systems that are seemingly stable can suddenly become unstable. So what happens is, for example, in the case of an avalanche or in the case of a sand pile, you have sand that's being poured into a system, and when it's being poured on top of it, or in case of snow, when snow descends on the layer of the top, it reaches what is known as a critical state. A critical state is very simply, in a dynamic systems theory, a state at which the system, with a little perturbation, can change from one state to another. So, for example, you can have a critical point where a stable becomes from stable to unstable, or from one stable state to another stable state, but this can only happen in a critical system. So critical basically means to the property of a dynamic system where it can readily change state if slightly perturbed. So for an avalanche model, if the system reaches this point where it's at a critical point, if you then keep adding a few more grains of sand, suddenly this avalanche will occur and the system will revert to the previous stable state. And you can keep doing this over and over again. For critical systems, that means they have a certain set of properties, and I'm going to argue these three properties are essential to the next part that I will talk about. Namely, we have a scaling of the system due to external perturbation, and this has to be non-trivial. And the scaling will mean that it doesn't matter how big my sand pile is, the properties of this critical system is the same for a small pile or for a large pile. So in other words, if you're playing on the beach with a pile of sand, you can show that the system behaves critically. But if there's a really big pile of sand, for example, here, this mountain is being created here, the property still applies. It's fairly scale invariant. Now, there's a lot of discussion within this area in physics about what that actually means. So I'm not going to go into that now. But it is undeniably true that a system that has a few elements of this property must persist at any scale. That means also at small scale. So if I would scale the sand pile down to really a few grains of sand, that would still be the case. We can express this in terms of a spatial temporal power law correlation. So power law correlation is a type of correlation where you have a constant raised to a certain power. And this shows you the scale of the level that can be operated. And of course, the system needs to have this self-tuning. So it's not just a matter that I have some supervisor that tells the system how big the Senpile needs to be stable, the system will choose the appropriate stable state for circumstances by itself. And this is what we will aim to achieve. Let me introduce you to another model. This is known as the Berry model, and Berry model is a biological model of the formation of extracellular matrix based on certain type of filaments, and this filaments then converted by two enzymes into a matrix construction, or deconstructed from the matrix construction back into filament. I'm happy to go into detail on this equation if anybody wants to know more about this, but I just want to show you that this model is in fact chaotic. But again, with rate control of chaos, we can stabilize it from this blue orbit here, which is the chaotic representation, to the yellow stable orbits here. On the right, I'm just showing you that it actually is stable. Now, what happens if we have not just one of those models, but we have lots of them? So what I'm going to do is I'm going to use this basic model to create this self-organized critical system by having a whole network of them. So you should just see them as a pool of oscillators that are connected together and create a complex self-organized critical system. So in this case, here I have 16 of them, and on the left here you see all 16 of them plotted. What you should imagine what these colors mean. These colors are the individual stable orbits, which after some time steps have evolved. I perturb the system using a random perturbation. So each of those oscillators is basically given a little edge. So on the blue here, you can see an example of this time evolution of the total of these systems, where you can see that it's nicely stably orbiting. Then the perturbation occurs, it finds a new stable state, orbiting in that state, etc., 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 etc. So we can do this indefinitely, as long as you want. On the left, you can see the matching orbits just with the transients moved, showing you that each of those orbits actually is different from each other. You will see that the columns are the same. And that's because the perturbations are done only on on each of the 4 columns in the same amounts, just to not make the system look really, really weird. On the right, this phase space representation here shows you the same orbits as the ones shown above, but then of the unweighted sum of all these orbits on the left. So all 16 sums of these 2 variables are added together, and then you get these orbits in different dimensions. So each of those colors is one of these orbits here. Okay. Now that's all good and fun. Very nice, but what can we do with that? Oh, sorry, I went the wrong way. Well, as it turns out, this actually is the basis of how a critical system can emerge. Because as I showed you before, the rate control of chaos method doesn't actually remove the chaos. It still behaves in a slightly chaotic nonlinear way when perturbed. So in other words, these perturbations, these little pushes that you give to the system, causes the systems to move to a new state and find a new stable orbit in which it can still be dynamically stable, in the sense that it will be a stable periodic oscillation. If we push, for example, in time, so we do the same exercise again, we have 16 oscillators and we perturb them again, but at the same time we change the strength of connectivity between the oscillators. In other words, we start with a very low minimum amount of connectivity, and we just change the connectivity of all of them. And then we increase this stepwise, and you see that these oscillations become bigger and bigger and bigger, and they're sort of plotted down here as well. So you can see from smallest perturbation all the way to the maximum perturbation, you see this sort of grows very quickly. You can also see that some of those orbits are a little bit more vague, not as neat, as well defined, but they still are distinct parts of the phase space. I can go in greater detail of what that means in terms of the control and dynamic stability, but I just want to continue carrying with the story, and I can come back to that if you have any questions about that. Now, can we quantify this? Can we say what does this actually mean? Is it actually emergence of criticality, or is just, you know, a simple network of oscillators that grows linearly? Well, what we can do is we can calculate to see what power law relations are. So what we do here is we take, for each of those stable orbits, we just take the maxima of the peaks of those orbits, and we plotted them against the perturbation. The amount of perturbation is here indicated with the symbol epsilon, against the maxima of the total oscillation. And here in blue, you see the peaks of those orbits. And then we can just do a curve fit on top of that. And then also the best curve fit for this system is indeed an exponential one, in this case 3.9 for epsilon to the power minus 0.13. Not tremendously strong exponential. And you could argue that maybe a power law can maybe fit, but maybe an exponential law might fit as well. And we'll look at that in a moment. On the right-hand column, there's something called a Gujarat Test, which basically calculates to see whether or not the power law fit is actually a good fit, good representation fit for the system. But we can also prove it in a different way. In the figure on the left bottom corner is what we do instead of having finite element differences between each of the connectivities in the oscillator. We apply a linearization to these connections. In this case, we use a Crank-Nicholson interpolation of the connectivity between the oscillators, which basically means a smoothing of the connectivity. And in effect, of course, that removes the nonlinear elements of the connection. So the information passed from one oscillator to another has become nonlinear. And when you do that, you'll see that this property of this exponential growth almost completely disappears. So we do the same experiment, still have the same oscillator still being perturbed in the same way, but the information passed between the oscillators is smoothed out. We can go in a bit more detail here and see that for the same type of oscillators, in this case, we have still our 16 oscillators that behave in this way here. And we can see what happens when we change the amount of perturbations. In other words, we still, in this case, we have a fixed connectivity using a finite difference connectivity scheme. And we change from smaller steps to bigger amount of perturbation for all of the oscillators. And this is then what you will see in the oscillators. If you plot the maxima of the two variables f and m that I showed you before against each other in the phase space, you see there are two domains emerging. There's this sort of looks like a linear domain almost here, and we have this cluster here on the right-hand side as well. But if we plot it in of the perturbation versus the maxima, you can see clearly that there is this power law emerging here on the left-hand side for smaller values of this perturbation term. And when it reaches this amount of perturbation here at about 0.045, which is subject to the amount of perturbation based on the design and the implementation of the particular oscillator, it switches to this scheme. So this right-hand side here matches this cluster here, and the left-hand side matches this scaling here. To see whether or not this actually is a power law relation or an exponential relation, we simply plotted for both of them the power law fits for all of them. So in red here we have a power law fit here on this data line here, which fits quite neatly. The orange one is the power law fit on the right-hand side of the data. And we also fitted an exponential function and on both of those. And you see that the blue exponential function, which is fitted on the left-hand side data set, is not nearly as good a fit as the power law. This sort of suggests that this is indeed a power law relation that emerges from the connectivity of these nonlinear interacting systems. It also shows you that the perturbation is essential in determining whether or not the system is actually within the power law domain or actually isn't in the power law domain. That's sort of the background about self-organized criticality and how I create that to create a system that has properties of self-organized criticality. But what I haven't shown you yet is that the system, because it's controlled by the rate control of chaos, is still deterministic. In other words, for each perturbation, there's only one orbit it will find. In other words, if I apply the same perturbation to the same network, it will always go to the same place. And that's the element that I'm going to exploit in the third part already of this seminar, where I'm going to use that to create nonlinear representation spaces for data. And why is this a good idea? Now, I've decided to call this criticality analysis on a simple idea that it basically allows you to use criticality to determine whether or not systems are well represented. And you can then use these nonlinear data representation to apply categorisation and classification algorithms much more efficiently. Now, this is basically the prime idea behind criticality analysis. I'm not going to and this is based on a set of oscillators of the Reservoir model. But this is basically the idea of why this works. And, I'm just using this figure here to illustrate, this is not actually real data, it's fake data, but basically to illustrate what the principle is here. So on each of these columns here, you see the orbits of the network of, in this case, 4 Reservoir oscillators are connected, and the maxima plotted against of both the x and y variable in this case. And when you change the connectivity of the system, you can see it changes a lot of its same behavior. So the data is the same, but the shape of the representation of the network is completely different. And that's basically the idea behind criticality analysis. So what we're going to do is going to create networks of oscillators and then perturb them with data and see how the system responds to this data in a dynamic sense, which allows us to basically say where each data is being represented by a particular orbit. Let's use a very simple.
Tjeerd, can you elaborate a bit more? What do you mean by saying that it is controlled or modified by the data? In practice.
So okay, yeah, no, thank you for that. Yeah, so you have to remember what we're having here is a network of nonlinear oscillators that are still rate controlled by the control method, and the domain is still in the codec domain, but they are stable individually. So the rate control basically causes the system to still be stable. But what we then do is say, well, we give them a push with these small perturbations. And that means that the system, just like the Senpile, gets pushed into a different orbit than it was without the push. So you should see it as by the data is the amount by which you push it. So we're basically saying to the system, you are in a stable state. We push each of those oscillators into using perturbation, and then the system will need to find a new stable state because the previous stable state wasn't stable for that particular system. So you should imagine that in a Senpile, I put some extra sand on it. This causes an avalanche, and then the system will need to find a new shape of the Senpile. That's basically the idea here. Does that make sense?
Yeah, a bit more clear now.
Okay. I do understand there's quite a lot to take in, and I'm going through it quite quickly, but I'm happy to go back and explain in much greater detail if necessary. So let's take a very simple data set, that everybody in machine learning is very well familiar with, very straightforward, well-known, namely the iris dataset. The iris dataset is a dataset that has 120 samples in it, if you download it from the machine learning database. It is 3 categories, 3 types of shapes of the irises as measured by 4 attributes, which are the width and length of the petals and the width and length of the sepals. And the sepals are the green leaves that protect a flower. And the classic example of this is because you basically have these 4 attributes and you basically want to classify them by saying which of the 3 types of flowers this is. So to illustrate how this affects a self-organized critical model, as I just tried to explain. So what we're going to do is we have 4 barrier oscillators connected using a fixed finite difference connectivity scheme. And what we do is we present to each of those 4 oscillators the iris dataset as a perturbation to it itself. So what I've done here is just simply on the left, we just plotted in the evolution of these 4 oscillators in time, which dataset is being clamped onto each of the 4 oscillators, so which dataset is being used. So we have color-coded them for the 3 types of flowers. I have to point out that the system doesn't know which category they are. Okay, so it's unknown, doesn't know which type of data is being presented to it. It just responds to the perturbations. So for the blue first sample set, it will stabilize into this orbit, and then we switch the system to the second data point, and then have a short transient. It will then switch to this orbit, etc., etc., etc. Here there are 2 samples that happen to be the same category. So this will basically illustrate what happens to the system. If we plot the total behavior of the oscillators against each other, namely total behavior of this variable f versus m, you can see it will sort of self-organize itself into 3 bands, roughly unique, where each of those bands represents one of the categories. So it's already self-clustering the data based on the property. And you can understand this because if the data samples are representing the same category, they must share a certain amount of properties with each other. In other words, they must have certain relations to each other that will cause them to be in the same neighborhood of each other. And that's exactly what you see here. You see that the green and the red ones, which are the 2 types of flowers that are difficult to linearly separate, and the blue one is the 3rd type, which is easier to separate. If we plot the maxima of these f and m against each other, you can see it even more clearly that there is here a domain where the blue and the green flower petals are sort of sharing space, but then it more clearly separates out each other. So it should be quite easy to see if I plot minimum maxima of this data, that if I create a linear separation boundary here, using, for example, a perceptron, that should be very easy to categorize. Yes, it's not perfect, but that's because the data is what it is. It's not actually that well separable in general anyway. But what I do hope you'll see here with this very simple example is that I haven't done any learning up to now. I've just chosen a set of oscillators, I've chosen a connectivity scheme that I knew would perform well, and then I just threw the data on it, and lo and behold, it creates a representation that is very easy for a classifier to work on. And this is basically the idea behind criticality analysis. I also mentioned earlier that this critical system must have this property of scale and variance. In other words, how well does it perform if it has only 4 oscillators, or if I have 64 oscillators? Now, if the system wasn't a rate-controlled nonlinear system, your data would simply disappear, it would just drown out in the behavior of the rest of the networks. But as we see here, for the 64 oscillators, it's still a critical system. And this shows you that the small perturbation by the 4 data attributes of the iris data still causes this entire 64 oscillator system to respond to these small perturbations, showing that this is indeed a critical self-organized system. You also see that the clustering is still in the same, even though, you know, of course, because I got more oscillators, the sum is much greater. But you also see that the separation is not as clean as it was, because of you cannot expect the oscillators to have no contribution to the total of the system. Well, what then, and this is just, I'm not going to spend too much time on this, but what then if you introduce learning? So I use another method that I developed called dynamic Habian learning to apply learning on the connectivities within the set of oscillators. And what you can see here then for each of the different categories, what actually changes not so much the amplitudes of the order, but actually the frequency of these oscillators is being changed. I'm happy to come back to this later, but I'm just use this as an illustration of that, how learning has an effect on the network. And this is important when I come back to my last slide of saying, where do we go with here? So I'm just going to skip this for now, but let me know if you want further explanation. This brings me to another concept, and you might be familiar with this concept known as reservoir computing. Now, reservoir computing is an idea first introduced as an echo state machine by Jaeger, and also Wolfgang Maas came up with a similar formulation of this known as liquid state machine. But it's basically the idea that if I have a neural network of stable neural systems, you know, this classic alpha function neural networks. And what I do is I create a large pool of these networks, and then I just present input on this network. And the idea is basically like in a pond, if I have connectivities within the network, and when I throw a rock into it, it creates a pattern, and then I train the output neurons to recognize that pattern. And obviously, because I have random connections between these the neurons, I will get different patterns for different types of inputs. And there's a very nice theoretical proof that shows that we can represent any amount of data in it if this pool of reservoir is infinite size, which of course is slightly of a problem. So we can do the same idea here. So we have, in fact, a pool of oscillators that respond uniquely to perturbations of the input. So if I then do that, so what I'm here created is a 4 oscillator reservoir, which fixed connectivity, and then I have 2 readout, readout oscillators, readout neurons, that will basically create a representation based on the input. In other words, I have a pool of four oscillators that respond to the input, and then I have a pool of 2 oscillators that respond to the behavior of the oscillators. Same idea. Sorry, same idea, just like in a feed-forward network, you have one layer, and then you have another layer that responds to the behavior of the previous layer. And to illustrate this, I've got quite a few figures here, but the blue, green, and red are just representing the 4 behaviors of the oscillators depending on the individual categories. And you can see that the behaviors look somewhat similar of the oscillators when perturbed with the same data. And here we show you in this figure here, we show you one of the 2 oscillators, the readout oscillators. Sorry, excuse me. One of the 2 readout oscillators showing you the maximum amplitude of these 2 readout oscillators as plotted in the blue, green, and red behavior as well. Also plotted the frequency change of that oscillator against itself. Now, what you can see here is that, in effect, what happens, for example, this is done, sorry, I should have mentioned that here in this figure here, I plotted the other oscillator. What's the difference between two oscillators? These two oscillators take input from the previous layer, but also from each other. But one of them takes input from the x-axis and the other takes input from the y-axis. So they just look at slightly different aspects from each other, but just might slightly look different. What I hope you immediately see that function f8 has a similar shape as the original one. In other words, I have a dimensionality reduction here, where the behavior of this one oscillator, namely 8, is similar to the total behavior of the entire network before. So I've showed you previously. Now you might argue, okay, that's all very nice, but it's all very convenient that this particular network behaves in exactly this way. So maybe you have a special oscillator that just happens to behave very nicely. That could have been the case, but it isn't. So what if we change the oscillator? So I now change the oscillator to something called the Wu system. The Wu system is basically a four-dimensional version of the Lorentz system with an additional feedback loop. So it's in fact a Lorentz system model. And in this case, the control is applied such that the system actually stabilizes into a stable state. So not an oscillator, but just to a stable point within the four-dimensional space that is embedded within the Wu system. So when I see, for example, here in evolution, here you see each of the three categories of the iris data. And when it stabilizes to a particular point, I just switch to a different type of orbit. So in effect, these arches here represent the transients until it reaches the stable point here, here, and here at each perturbation. Yeah. So a question? No? Okay. And here on the right-hand side, I have these stable points plotted against the Y, Z, and W orbits of the four-dimensional Wu system, so three-dimensional representation of the four-dimensional system, showing you that just like in the Berry model, we have, in fact, a clustering of the system because these points represent same types of data. And you can also easily see that it shouldn't be difficult to find separation boundaries here. Okay, this is another slide track, which I'm going to skip for now, but I'll come back to it. But basically, we're saying what happens if you use a higher number of attributes data set. In this case, I use the line data set rather than a four-dimensional data set. I've got 13 attributes. And what happens is as a network. I'm conscious of time, so I'm just going to move on. Okay, now, I hope I've sort of convinced you now that we have a reliable system to create representation spaces in a nonlinear system of data. So what if we actually use it for real data? So I'm just going to show you the illustration of here. So in gate data, human gate data, what you do is you put an accelerometer on the center of mass of a person and you basically measure the X, Y, and Z acceleration of this person in real time. And this was the idea here that once we do this to individual gates, what we can see, you can actually use this to determine for the same person in this case, whether or not they are walking normally or they're being impaired. And the blue and the red ones show you the what happens when somebody has a strap on their leg to make them limp a little bit. So you can actually see the difference between those two orbits if we present the data directly to a set of connected oscillators. I can talk more about this, but I just want to quickly introduce, and then I give you in a couple of minutes, give you a chance to ask further questions, but I'm conscious of time. This is based on collaboration with Dr. Patrick Esser and Professor Helen Dawes of the Motion Science Group. And what we've done basically is we completed the cycle. We created a critical analysis system of gate data collected from normal people of different age categories And then my research student, Tjeerd V, has added a support vector machine on this critical analysis data to categorize these gates into the different categories. And as you will see, so very quickly, this data was collected from volunteers that visited the Science Museum, and we have 5 different categories. We got almost 2,000 data points with a fairly decent size of data, separated in gender and in age. And so when we apply this to the criticality analysis, on the left-hand column, you see the oscillation itself, which is not very informative. But what is more informative is the maxima of the histogram in the middle. You can immediately see that different age groups or the male group show that these behaviors are not the same for each categories. So if you then apply and the same for the females, a support vector machine, in this case, the radial basis function on it, we can actually create a fairly decent, or actually a very good separation of the classifications between groups. In this case, we compare, for example, children and adolescents. And this is where I'm going to leave it. I can show you for comparison between all of the categories, but I'm just going to leave it here in case there are any questions for that. And just sum it up for now, because we're almost out of time. So what have I done so far? I've recreated this method of rate control chaos that allows to control nonlinear complex dynamic systems. We have applied this as a means of creating homeostatic control, namely to use local dynamics to cause global stability. This can also be used to create unique representation spaces. I hope you've seen that somewhat. And the particular application here is to apply this to biological data, and we can add things to it to make it more interesting, namely like dynamic learning and the concept that I am working on now, which is known as dynamic Darwinism. But this is everything I leave for now, and here are some references of the work that is described as now. So if you have any more questions at this point, I'm sorry I took so long, but I hope it was informative. Thank you.
Thank you so much, Tjeerd, for your very, very extensive and nice presentation. We had a few questions in the middle, but now let's open the question part of our seminar. So whoever wants to have a question, just switch on your mic and ask a question. I have one or two, but I leave the space for others.
Hello?
Hi, Stefan.
Hello.
Oh, I was not muted before. My God, I hope you didn't hear background noise. So yes, thanks a lot for the presentation. It was really outside of what we're used to and very inspiring, I would say, the best word for me. And so I have a question, and it's going to be stupid because I really need to learn the basics to me in order to be able to follow. So 2 questions. One is about the types of oscillators that you think what you're working on can be limited to, if there is any limitation. And the second is, I see some applications in the field of fracture mechanics for especially self-organized criticality. When you have loaded cracked surfaces, for example, in fracking applications or in applications where the crack faces are loaded by some sort of pressure coming from either fluids or air or gas or anything else, because then the pressure piles up, and after a while it's like literally piling up like a pile of sand, and you apparently get very similar behavior. And I wonder if you know whether people have used what you've done to examine such cases, and if you have any comments on that. That's it.
Okay, well, thank you for your question. Let me first ask the first one. Nothing is perfect, not even rate control chaos. So there are limitations, and limitations are based on how well the system can respond to the perturbations. So sort of crudely said, the more nonlinear the system is, the more representations you can create. So in other words, you can sort of imagine if, like, for example, in the raster system, it's only one point of nonlinearity, the density of the system, how much space it occupies, also means that, of course, how much separation you have is limited because it cannot occupy any of the other space. In other words, it doesn't create a new, attracting shape, so that the domain of attraction will remain the same. And if the domain of attraction is small, it cannot create a new one. So that's a sort of limiting in that sense. And I'm also conscious that some data might not be very well represented, and again, the system only responds to perturbation. That's all it does. It doesn't create information, doesn't tell you anything about the information in that sense. So anything that you want to apply as learning or categorization on top of it, you still need to do that. And then second, your question about fracking. Actually, when I started out looking into self-organized criticality, I spent a fun week in the Bodleian Library in Oxford, looking through the literature regarding self-organized criticality, and I was quite a lot from the geologists about this property. I don't think I've learned much about geology, I'm afraid to say, but what I did gather was that there are models out there that could be applied to this type of thing, but geologists are not actually, in my view, that interested in this property of self-organized criticality. To them, it seems to be a nuisance, something that they rather avoid. So there might be some direction in saying, well, can we re-examine those models in this light and see whether or not they can be applied? But that's all I can say. I'm not knowledgeable enough in this area to say immediately that they will be useful for this particular type of model.
Jakub, can I ask a follow-up quickly?
Yes, yeah. Sure.
Thanks. Sorry, just a quick one. What would be the minimum information you need in order to start analyzing the system? What do you start from typically?
Okay. I hope maybe I haven't mentioned this explicitly.
No, maybe I didn't understand it more likely.
But the control method is key here. Without the rate control of chaos, it simply doesn't work. And that's because it basically, I have some other models that I can show you that shows you that what happens, and this is the whole idea behind local control in homeostasis, for example, to create a global stable system. What happens if you have local interacting systems that cause instabilities somewhere else? So you can sort of imagine in something called spatial temporal chaos, which is quite common, is where you have local elements that are individually stable, dynamically stable, but because they are connected to each other, they cause a global instability. And this is the idea behind, the wave patterns, for example. Product wave patterns are generated that way. The whole point here is that, and I've got some other modules that's also published in my 2017 paper, that shows that the rate control of chaos prevents that from happening. So can allow that to happen. So in short, what model should work? It should be a model for which we can apply this method and therefore create a cluster of oscillators that allow you to test this hypothesis.
Okay, thanks. I'll shut up for now. Thanks a lot.
Okay, thank you very much.
Tjeerd, may have a question because we are working with SORAP on stochastic neural networks, and somehow your liquid state computer idea that you shown on one of the slides somehow resembled me, the stochastic system. But in your case, there are some interconnected oscillators that are connected by some elastic link, or this is a nonlinear link, or I don't know.
No,
And then somehow I see some similarities between the two. Are you aware of any work that dig more into detail into these similarities, somehow interpretation of one with respect to another, neural network or stochastic neural networks versus these type of computing systems, or could you
so actually three different elements here, I think. So there's this idea of reservoir computing, which was suggested by Wolfgang Maas from Graz University in Austria, where it basically shows that this idea of where you have random connections basically allows you to create patterns in the reservoir, which you can then train another network to recognize those patterns. So it's sort of indirect evaluation, which is, and I'm just using it here as a similar idea that in my criticality analysis model, you use the same idea, but the patterns you generate are not produced by random connections, but produced by a dynamic system. And in my case, of course, the dynamic system is fully deterministic. So if you have a network with known fixed connectivity, so the connectivities can be varied, and it's one of the slides was about what happens when you vary them. But in all of these models, those connectivities are fixed. So all we're doing here is throwing the data on this network and then observing how the network responds to this data, and then use that to categorize the data. So it is fully deterministic in that sense. So once you fix the network and the oscillators and the connectivity and you throw the data in, it's just the data that determines what orbit will emerge. And that's the basic principle that causes you to create those clusters of patterns. What happens, there are people who've created models of self-organized criticality based on stochastic models, and that is because it's a lot easier to create self-organized, provable self-organized criticality system using stochastic models. Because because you're basically causing one system to become non-linearly more responsive than another. So the more stochastic elements you have, readily the system can fall into a new critical state. How does it apply to neural networks? I am aware of some work, as you undoubtedly know, to do with clusters of stochastic networks with the same idea. But one of the reasons I moved into deterministic and basically in chaos is to move away from stochastic methods. So in that sense, I'm sort of going in a different direction than you, because I sort of lost my confidence a little bit in this type of approach because of this lack of determinism, in the sense that, what happens if you perturb the system and then later on you have slightly different network, weight matrix due to the stochastic perturbation, and then the response can be different again. So I was trying to avoid that aspect of system, but it doesn't mean that it has no, as far as concerned, it could still be used. An interesting aspect which I haven't shown you of this method of rate control of chaos, it is fairly noise robust. In other words, it will change the orbit, but it will absorb the noise, because you can see, for example, that the data, if the data is noisy, it still works, but you can see it still orbits within the same domain. So I think there's definitely something there that I think I would like to explore in the future, but to say exactly at this point how this is going to respond is beyond me at the moment.
Okay, thank you so much, Tjeerd, for your response. And any more questions? I know that we are a bit behind the time now, so some people just left for another meetings.
Yes, I have another question. It's a bit weird question, so maybe maybe it won't be clear. So we are in the field of computational, let's say physics or mechanics, and we have couplings between different fields usually. And what also happens is that sometimes some solution, let's say that we solve a coupled thermomechanical chemical problem, let's say, so that we have three fields defined on space, and there are maybe vector fields or scalar fields, depends. And some of them are computed by code A, the second one by code B, and the third one by code C. And three codes are independent. And then the solution to these problems are, let's say, spit out by three different codes and have to be put together in order to find a solution to the coupled set of partial differential equations which governs the system. And I was wondering, because so there are some stability issues in these systems which have nothing to do with chaotic systems at all. But what I was wondering is whether you heard of applications in that area where the system itself is not supposed to be unstable, but it becomes unstable because of numerical issues. And what I'm wondering is whether that can be formalized in a way that you could control the instabilities using some sort of control algorithm, which is not what we use usually. But I'm just thinking completely out of the box at the moment. I mean, not at all. I have no clue if that makes any sense. And in that sense, that's why also I was asking before what you need as an input in order to figure out whether that has any sense. Do you see roughly where I'm coming from?
Yeah, I think well, I'll try and interpret it in a way that I think so makes sense to me. So then, if you please correct me if I have the wrong end of the stick, so to speak. I have looked in the past when developing the rate control care, specifically in detail about this concept of the causes of instability. That is quite extensive literature in nonlinear dynamics, mathematics, about different ways that system becomes unstable or go to different transitions, different even catastrophic type of decision. And I have a friend of mine who still works in catastrophe theory about systems suddenly develop singularities, for example. And what I got out of that was primarily the issue of how sort of variables can become, there's something called parameter changing. So where variables basically become fixed in a particular domain, and then the associated parameters suddenly can become bifurcation parameters, even though they weren't. So there are domains of bifurcation possible. So in the classic theory of bifurcation theory, as defined by Smirnov and people like that, you're basically thinking about that a parameter is either a bifurcation parameter or a perturbation parameter or stable parameter, and they don't change. But it seems that on some cases they can change and can become suddenly become relevant for a particular bifurcation. And it has been suggested in self-organized criticality that this might be a property why suddenly systems reach this state. So this idea basically of onset of critical state or onset of synchronization of a critical state due to the fact that you have enough elements that will cause the system to be suddenly become critical as opposed to other. I know visitors sort of think about this, about why things like, for example, actually this was from geology, how quicksand suddenly develops out of nowhere, because it suddenly reaches this critical state. That's basically all I have at this moment. So I am aware that there is a problem, but I haven't really thought about how this could be applied.
Yeah, because what made me think about it is that when you analyze these numerical schemes, you do something similar to a perturbation method. So you perturb the solution by some exponential, and then you see if the perturbation grows or decays. Basically, that's the way you analyze it mathematically. And then I was thinking, perhaps there is a way to use what you're doing in order to stabilize numerical schemes, which are artificial. They are spurious oscillations. The ones you see, they are not real. They are not physical. That's why we don't want them. So we would like to get rid of them, and not to, not to analyze. I mean, not to see them, but we don't want to see them and know where they are going. But I mean, somehow I thought maybe there is a connection there.
Yeah.
And yeah, and I don't know, obviously.
No.
That's
I think there might be something there, and that would be interesting to look at that.
yeah. Okay. Anyway, thanks a lot for taking the time. Really appreciate it.
Thank you for having me. Thank you very much.
Okay, thank you again, Tjeerd, for your presentation and answering our questions, for your time. And I hope that we'll stay in touch. Let me welcome everybody for the next week for another machine learning seminar. And thank you for your participation today. And have a good day. And see you. Bye-bye.
Okay. Thank you very much. Bye-bye.